In this lecture video, we will cover phase diagrams. Please read the OER textbook chapter section 10.4. Phase diagrams are combined plot of pressure, temperature, and physical state of matters. So here is an example of diagram of water. So as you see here, the plot is between pressure and temperature, and also it's going to include the physical state of matter as well. So on this side is going to be solid, and in the middle would be liquid, and far right is going to be gas. Okay, so the one that beyond this point right here is what we call supercritical fluid. Supercritical fluid is going to happen when there is no boundary between liquid and gas. Supercritical fluid is going to behave like gas and also like liquid as well. For example, it's going to be able to effuse through the solid like gas, and it also can dissolve the material like liquid as well. Okay, so we're going to see more the application of this in just a few minutes here. The boundary that separates between solid and liquid is what we call fusion curve. And within the fusion curve, this is where solid and liquid are going to exist in equilibrium. Okay, so within this point, you are going to find liquid and solid in equilibrium. Okay, so if you're looking at 1 atm pressure, and if you looking at the temperature at this point, this is what we call this point normal melting point. Okay, so water would be 0 degrees Celsius. Okay, and if you're looking at the boundary between liquid and gas, this is what we call vaporization curve. Within the vaporization curve is when the liquid and gas exist in equilibrium. Okay, so both of them are in equilibrium, both liquid and gas. And if you're looking at 1 atm pressure, the temperature at this pressure is what we refer as normal boiling point. For water, it would be 100 degrees Celsius. Okay, and the boundary that separates between solid and gas, this is what we call sublimation curve. And within the sublimation curve, you will observe solid and gas exist in equilibrium. Okay, and when all of these three phases meet together, this is what we call triple point. Okay, so this point going to have 3 states exist in equilibrium. Okay, and the last one is the critical point. Critical point is the last point where you are beyond that, beyond that you will no longer be able to separate between liquid and gas. Okay, so beyond that, it's going to become supercritical fluid. Okay, so if you do the transition between solid to liquid, this is when the melting or fusion happen, right? The reverse process of that would be freezing, right? So that means in this case, if you do at a constant pressure, right, you increase temperature, it's going to melt, right? If you decrease temperature, it's going to freeze, right? According to the temperature axis right here. Okay. Now, same thing, if you continue increasing temperature more, you are going to cross the phase transition from liquid to gas, right, vaporization. And if you do the reverse process by reducing temperature, right, so this is temperature reducing, you are going to end up with the process of condensation. And according to this graph, you can see that at low pressure, if you increased temperature, you can also going from solid to gas as well. Therefore, in this case, you can do sublimation under low pressure, and vice versa, right? So at low temperature and also low pressure as well, deposition will occur in this case. Please note that the phase transition also occur when pressure change as well. For example, if you have solid water at a certain temperature, as pressure increase, it can change from the solid state to liquid state as well. Now let's take a look at the application of phase diagram of water. So one major application is in freeze-dried foods. So foods contain water. So in this process, it's actually involved with how to remove this liquid water, right? The process is going to involve with freeze and dry process. So we are going to start with liquid water. As the temperature decreases, so going that way, as the temperature decreases, it's going to cross this boundary right here, going to the solid, right? So that's the word freeze means here. So that means this process is going to involve with reducing temperature, right? Make it cool, make it cold, right? And the word dry is going to come from the fact that as the pressure decrease, okay, so we're gonna decrease pressure. As the pressure decrease, the solid water would then cross the boundary and it's going to go from solid to gas, and it's going to be the drying process. Okay, so that means in this case, this process right here is going to involve with reducing temperature and also reducing pressure as for the freeze dry process to be achieved. Another application of phase diagram of water is going to be used in ice skating. So in this case, you will see that the blade of the ice skating shoes right here is going to put pressure on ice. And if it have enough pressure, it's going to cause the ice to melt. If you're looking at this diagram, right, so at a certain point of the ice, right, if you have enough pressure, which means you are increasing pressure, that's going to cross from solid to liquid, right? So this process right here is going to allow for the ice skating shoes to be able to glide on ice. Phase diagram will look varied depend on substance. So here is another example. This is the phase diagram of carbon dioxide. So you see that it's look different from of water that we see previously, though we will still observe the solid, liquid, gas, and supercritical fluid here. Supercritical fluid of carbon dioxide has been used extensively in extractions, especially in decaffeinating coffee. The reason for that is because the supercritical fluid of carbon dioxide is easily available, is inexpensive, non-toxic, and also non-explosive as well, and also is allow for the moderate condition of the extraction for the temperature to be not greater than 100 degrees. And here is the process of decaffeinating coffee using supercritical fluid of CO2. So it starts with soaked coffee bean will be fed through this extraction vessel, and the supercritical fluid of CO2 will pass through this extraction vessel. As I mentioned earlier, supercritical fluid going to have the property like gas and also like liquid as well. The gas property would allow the supercritical carbon dioxide would be able to pass through the solid of coffee bean. Okay, so as it's passed through the solid of coffee bean, it's also going to dissolve the caffeine molecule from the coffee bean as well. So therefore, in this case, it's going to be able to flush out the caffeine and carry it with it, and leaving the coffee beans to be decaffeinated beans. Okay, so, and then this supercritical CO2 will then carry caffeine through the absorption vessel, and water will be fed into this vessel to pretty much dissolve caffeine with the water, and then feed the carbon dioxide, supercritical carbon dioxide back to the extraction vessel again. And this is just one of many applications of supercritical fluid extraction. Now let's take a look at example problem that you are going to see on the exam. Okay, so let's take a look at this problem right here, asking us to figure it out which statement below is true. Okay, so let's take a look at A. Okay, so A said that the triple point of this substance, okay, so this is the triple point, occur at temperature of 31 degrees Celsius. This is temperature, so if I look at the temperature, it is not at 31 degrees Celsius. Okay, so this is false. Okay, if you're looking at 31 degrees Celsius though, if you go all the way here, this point right here is what we call critical point. Okay, so this is critical point. Okay, so this is called triple point. So they are different. So that means A is false. Now let's take a look at B, right? So at ATM of pressure, okay, so it's going to be around here because this is 7.3, this is 5.1, so it's going to be around here. It said that at this pressure right here, there is no temperature where liquid phase of this substance would exist. Okay, that is not true, right? Because if you're looking at this, right, so at high temperature, right, so between like around here, right, so that is where liquid phase will actually exist, right? So there is a temperature to allow for the liquid phase to exist. Okay, so B is also false. Okay, now let's take a look at C. Okay, so C said liquid phase does not exist at the pressure below 5 atm. Is that true? So this is 5.1 atm. And we're looking at this, right? So this is 5 atm. If we're looking at this pressure, it said that below this pressure, okay, so anything below this, we will see that there is no liquid phase. That is true, right? Because if you're looking at this, right, below this 5.1 is only solid, right, and gas that exist. So in this case, it's only solid and gas exist. So C would be true. Okay, so again, the reason why C is true because under this line right here is only solid and gas exist. Okay, so C would be the answer for this one. Now, before we move on, let's take a look at why D and E, why D is incorrect. Okay, so D, the reason why it's incorrect is said the line separating the solid and liquid. Okay, so the line separating solid and liquid is this line right here, represent the delta H evaporation. This is not true. Okay, so the line that right here, right, is actually fusion, right? It's the fusion curve. So the heat that involved with this is going to be the delta H of fusion, okay, not delta H of evaporation. The delta H evaporation will occur between liquid and gas. Okay, so this one right here would be delta H evaporation. So D is false. So that means in this case, the correct answer of this would be C. In this video, we learn about the phase diagram, especially of water, and also we look at the application of the supercritical fluid of carbon dioxide as well. Please start working on homework 10.4 as soon as possible. And if you have any question, please do not hesitate to visit me during office hour.